We are going to be talking about systems of equations. And what we want is a method for solving systems of equations. Are you familiar with the term algorithm?
Yes.
Okay, right. And I think about it like long division is an algorithm. You take any two numbers and you want to divide them by each other. There is a way of doing it. There are a set of instructions or a set of rules for how you go about doing it. And no matter what two numbers you have, you just follow these rules and eventually you'll get an answer. Now, it's not always easy, right? It's not always the easiest thing to do. Sometimes it's difficult, sometimes it is easy. But the cool thing is that it's always going to work, right? And so that's what we want with systems of equations. I want to be able to take any system of equations and find the solution using the same method every time. And so on one hand, that method, so there are a lot of methods for solving systems of equations. And sometimes the method that we use will be way easier. Usually, and I'd say most of the time, it's going to be about the same amount of work as any other method you use. Sometimes it will be more work than using one of other methods, but the payoff is going to be that we never have to sit there and wonder which method should I use. Oh, this is this kind of case. And so we just start plugging along, and by the time, even if you're doing more work, by the time you're done, you're done. Whereas with the other way, if you're trying to figure out which method do I use, now you've just wasted a bunch of time when you could have been calculating. So again, sometimes the trade-off is going to be, oh man, now I'm adding fractions together or something like that. And that could get a little tedious and ugly. But I think this is the best way of solving systems of equations. Now, we're not going to talk about that method today unless we happen to get to it. But what I want to do is build up our reasoning towards that. Like, I don't want to just explain the method to you and then, now just memorize this. Because that's the same thing as saying like, well, here's the point slope form of a line. Now just plug stuff in. I want us to believe that this method works, because then it'll like really take root in your brain, right? And we don't want to just memorize stuff anyway. We want to believe what we're doing. And so that's what I'm going to do today. We're going to start simple and we're going to work our way towards the method. In order to do that, we are going to just make observations about equations and what we do with equations. So let's start with an equation. We're going to say, okay, we have this equation. Do you believe that equation? Is that equation true?
Yes.
Right, okay. We start, so we have an equation that is true. Now, it wouldn't work if I had 1 + 2 = 5, right? Like, we're talking about a true equation. I'm going to be saying that a lot today, a true equation. That means that it evaluates that indeed, yes, on the left-hand side, you have 2. On the right-hand side, you have 2. Yes, that is a true equation. Now, one thing we could do with a true equation is we could rearrange it. So like if we have addition and subtraction and stuff like that, we could move stuff to either side, right? So like explicitly, I could take this 1 and we say -1 from both sides, and we get a new equation, 2 - 1. Okay. Okay, so in other words, I've just rearranged the equation and I got a new equation. Is the new equation true?
Yes.
Right, okay. So I'm starting to see here's an observation. We're going to make our first observation, and I'm going to write it like this. We can rearrange. Rearrange and I'm just going to put a big capital T for true. Rearrange a true equation, and that gives me a new true equation. We take a true equation, rearrange it, and we get a true equation. Okay, So that's observation number one. Now, do you believe that that's going to work for any and every equation? Like if you start with a true equation and you just move some stuff to one side or the other, does it remain true? Seems that way. I mean, I'm having a hard time.
Probably.
Right? I mean, and yes, like things get tricky and you know where we're going with this. We're going to systems of equations. So it's like, well, I'm not sure. And that's a good answer, right? Like probably.
Probably.
That's a very good answer. But right now, this is how it looks. It looks like this is true and it seems to be true, right? Like what we're getting at here are axioms, really. Like an axiom is something like this. So like if you have A equals B, and you know that B equals C, it must be the case that A equals C. Now you cannot prove this, actually. There's no way to prove this. There's no proof for this. It's just so obvious that you're like, how could it not be? And so what we've done is we've just said, well, this is an axiom. It's trivial. It's like, we can't, I can't see any other way that this could be. And so we just take it as an axiom. It's like the foundation of stuff, right? This is kind of what we're doing here. We're taking something really trivial, right? 2 equals 2. Yeah. Subtract 1 from both sides. Is that still true? Yeah. I have a hard time seeing that it's not, right? Okay. So that's what we're doing. We're just trying to find out some stuff. Now, here's another thing we could do with that equation. I could take that equation, and I'm going to say this a bunch today and probably for the rest of the year. I'm going to say multiply an equation by. And what I mean is take a number and multiply both sides of the equation by the same number. But I'm just going to think about that as multiplying the entire equation by a number. And so let's do that. Let's choose a number. How about 3? And I'm going to multiply this equation by 3. And so here's my equation. And I'm going to multiply the equation.
Well, I don't want her to walk where we can't see her. So
that equation by 3. Now let's see what we get. I'm just going to use my rules for multiplying a sum. So we distribute the 3 into here. And we get, let's see, 3 plus 3 equals 3 times 2 is 6. Is that true?
Yes.
3 plus 3 is 6 last time I checked, right? How about, now I could have done that with a negative number. I could have put -3 on both sides. And we would have had, let's see, -3 minus 3 equals -6. That's still true. Okay, so positive numbers work, negative numbers work. What about 0? Let's see, does 0 work? Let's just try. 1 plus 1 equals 2. And now I'm going to multiply this equation by 0, meaning I'm multiplying both sides by 0. And hey, what do you know? I get something that's true. 0 equals 0. This brings me to my second observation, is that you can multiply a true equation by any number, and you get a new true equation. It might not necessarily be new if I chose 1 on both sides. If I multiply it through 1, it's the same equation, but you know what I mean. You've done something and now you have something else. Now that thing that you have is a new true equation. Now it's obvious, right, that if I start with a false equation, this doesn't work, right? Like if I had 1 plus 3 equals 7, and I multiply that by any number, how about 3? So I'll do that on both sides. And now I get 3 plus 9 equals 21. Well, if I start with a false equation, I end up with a false equation, right? So we're not interested in false equations. We're talking about true equations. Okay. Okay, so that's the second observation. Do you believe the second observation?
Yes.
Right? Makes sense. Okay. Now, here's the third observation. We have an equation. Hey, bud. And I'm going to make up a new equation. How about 7 minus 3 equals, what is it, 4? I think it's 4. We want
4.
Yeah, okay, good. So we have a new equation, a different equation. 7 minus 3 equals 4. It is true. That is a true equation. So we have two true equations. Let's add them together and see what happens. Let's just add them. In other words, the whole thing, what I'm saying here is on this side, you just have a number, whatever number that happens to be. On this side, you have a number, whatever it happens to be. And we could add two numbers together. And if I do the same thing on this side, should give me something consistent. So I'm just going to do this real quick. In fact, I'm going to do it in columns. I'm going to say, okay, 1 plus 7 is 8. And I'm going to say 1 minus 3 is minus 2. 2 plus 4 is 6. And now we have a new equation. And lo and behold, it's true. Right? I think 8 minus 2 would be 6. And so my last observation here is going to be that if you take two true equations, add them together, then you get a new true equation. So 3, we're going to say it like that. I want to make sure that's how I want to say it. Yeah, add two true equations, and we get a new true equation. Okay. These are going to be guiding principles for the rest of everything we're reasoning about here. Now, this was the case where we were using equations involving 0 variables. There's not one variable in there. In fact, everything we just said kind of makes you want to roll your eyes. You're like, yes, obviously 2 equals 2. Obviously 4 equals 4. Yes, obviously 6 equals 6. It's obvious in that case. There's no room for play. It doesn't matter where you are. These things are true. Like if I'm standing here, it's true. If I'm on Mars, it's true. If I'm in the Andromeda galaxy, all of these things are true. It doesn't matter where I am. But now we're going to add in one variable. Let's add in a variable. Let's say that, how about x equals, we'll do this again. We'll say 1 plus 1. Now it does matter where we are. And I don't mean like physically, like whether I'm in Seattle or anywhere else. I mean, what I mean is where on the number line is x. And so this is the x number line. As long as we are at the point x equals 2, that's a true equation. Okay? Like, and there's no other place I could be that's going to make that equation true, right? If I'm at x equals 5, that's a false equation. I have to be at x equals 2 for that to be true. But as long as it's true, it's a true equation. So let's just check our observations. Can I rearrange this and does it stay true? Well, I could rearrange this. I'm going to subtract 1 from both sides. In other words, rearrange and bring the 1 over to the other side, and I get x minus 1 equals 1. And we could say, yeah, as long as x is equal to 2, that's a true equation. And so do you believe that? Like, do you believe that this works for all equations with one variable? Do we get this right there? Seems like it's the case, right? I mean, I'll believe it. I'm not trying to trick you. It seems that way. Another thing, like we could say, I don't know, let's take 2x. How about 2x minus 3? And what should we get? Well, as long as x equals 2, right? If we're in the same place for x, we get 2 times 2 minus 3 is 4 minus 3. It should give me a 1, right? Yeah. Now, this is key here, that both of these equations have to be at the same x. You can't have x equals 2 in this one and x equals 5 in this one, and then hope that, like, for instance, if I were to write something like 2x plus 3 equals, how about 9? We could see that that's not the same. In fact, the only x that's going to work, and again, just like this was trivial, there's no room for playing around with 0 variables. Either 4 equals 4 or it don't. Here with 1 variable, it's also kind of trivial because we can see there is only one value of x that works there. In particular, if I wanted to know what it was, I could just minus 3 from both sides. I get 2x equals 6, I think. 9, 6, 7, 8, 9, yeah. And then I divide by 2. And I see that this only works when x is equal to 3. So if we wanted to add this equation plus one of these equations, that wouldn't work because we're not talking about it being at the same point. But these two work because we're talking about we're at the same point, so this is true. We're at that point, so that is true. And so let's just see what happens. If I add them together, we're going to add these two true equations together while we're at x equals 2. 1x plus 2x gives me 3x's. Minus 1 plus a minus 3 gives me a minus 4. 1 plus 1 gives me a 2. And let's just check. If I plug in a 2, I get 3 times 2 minus 4. That is 6 minus 4. Gives me a 2, and so we get 2 equals 2. So it looks like number 3 works actually, right? Add two true equations. They're simultaneously true. We're not talking about different x values because obviously that's not going to work. We have to be talking about the same value of x for them to be true at the same time or in the same place. But as long as that's the case, it's still trivial. Like you still have on the left-hand side of this one, you still have 1. On the right-hand side, you still have 1. On this one, you have, well, I happen to do 1. I could have done that for something else, but you happen to have 1 equals 1. And so what do you know? You add 1 plus 1 and you get 2. Yeah, that stays true. So, okay, we could rearrange a true equation involving one variable and it stays true. We could add two true equations and they stay true just as long as both equations are at the same point. They're simultaneously true. Let's try multiply an equation by any number. Real quick. Let's just do this one. We have 2x minus 3 equals 1. And I'm going to multiply this equation by, I don't know, how about 2? I'll do 2. Okay, so I multiply the entire equation by 2. In other words, I multiply both sides by 2. And I get, let's see, I distribute this in and get 4x minus 3 times 2 is 6. And I get 2. And we could say, well, yeah, is that still true at the same place? Yeah, if I plug in a 2 for x, I get 4 times 2 minus 6. 4 times 2 is 8 minus 6. What do you know? Still equals 2. We still get a true equation when we multiply it by any number. Even 0 is going to work because if we multiplied it by 0, we'd have 0 on the left side, 0 on the right side, and we'd have 0 equals 0, still true. So it looks like all of these observations work. They're still valid for everything we do involving an equation with one variable, just as long as we're talking about the same x, right? As long as the x in the first equation is the same x as the x in the second equation. And so, okay. Now, guess what we're going to do? equations involving two variables. Now, this is the conceptual jump, because really everything we've done thus far has been trivial. Like on over here with zero variables, we basically have stuff like 3 equals 3 and 5 equals 5. Obvious. Here, it's okay, it's a little bit different, but ultimately, with anything you write here, there is only one value of x that works, right? Like not knowing any of this stuff from before, if I just gave you 3x minus 4 equals 2, you'd say, well, the only value of x that could possibly work is x equals 2. There's only one possibility. So it's kind of like, in the case with no variables, there's 0 possibilities. It's always true. In the case with one variable, there's one possibility. But now with two variables, what happens? Right? And so I've been debating for the last few days how I want to go into this. But let's start, because in this case, I started with something like I knew what x value I had. Let's start with a known x and y. Let's say that my x is equal to 1 and my y is, say, equal to 2. So we're at the point 1, 2. Remember, the first stuff doesn't matter where you are, it's always true. This stuff, you have to be at a specific place on the x-axis. And now, for equations involving two variables, now we have two places we could be. I could be somewhere in x, I could be somewhere in y. So when we say where are we, we're talking about a point in the plane. In this case, it's 1, 2. That is, we're talking that x is equal to 1 and y is equal to 2. And so let's say that that's the case. And I'm just going to, I have not planned this ahead. I'm just going to make up an equation right now. How about 2x plus 3y? Well, if x is equal to 1, we have 2 times 1. And if y is equal to 2, we have 3 times 2. So we have 2 plus 6. Yeah, 2 plus 6 is 8. And so, okay, I'm just going to work we get here. And we can see that, yes, if we're at the place 1, 2, that is if x equals 1 and y equals 2, then this is a true equation. Let's get another true equation at this point. How about, we'll make it easy. How about x plus y? X plus y. Well, if x is 1 and y is 2, then x plus y has to equal 3. Okay, so let's add those guys together. We're going to add these equations. We get 2x plus x, that's a total of 3 x's. 3y plus y is a total of 4 y's. 8 plus 3 is 8, 9, 10, 11. That is 11. And now I want to know, is it still true if I'm standing here at the point x equals 1, y equals 2? Well, let's check. Let's plug in a 1 for x and a 2 for y, and we get 3 times 1 is 3, 4 times 2 is 8, 8, 9, 10, 11 is 11. Yes. Okay, so it looks like, and right now it seems like this is still trivial. It's about to not be in just a second. But my first observation is, if we're at the same place here in x and y, I notice that as long as we're talking about the same x and y in both equations, really, we're still kind of over here, right? There's only one possibility that this thing could equal, and it equals 8. And the left side equals 8. So technically, you have 8 equals 8. As long as we're standing at the point 1, 2, then 1 plus 2, that number right there is equal to 3. So it's still trivial. You have 3 equals 3. So really, you're just adding 8 plus 3 on both sides. It just looks, we've written it in a funny way. Just as long as we are at the same point in both of these equations, right? Like I said before, right? As long as you're at the point x equals 2 up here, and you're at the point x equals 2 here, then both of these are consistent and you get a nice true answer. So I want to say that this thing works, but I have to say, again, like I did before, as long as both equations are at the same point. But here comes the conceptual loop. So I'm about to erase everything except for our observations. Am I good to go?
Yes.
Right? Okay. So here we go. Here comes the conceptual. So it used to be the case that, like, when we had one variable, I could write an equation involving one variable, and there's only one possibility that could possibly make it true, right? Let's write an equation with two variables. How about x minus y equals -1? Now, we don't just have one possibility, right? We have infinitely many places on the xy plane where that is true. Like, for instance, how about 1, 2? If x is a 1 and y is a 2, we have 1 minus 2 equals -1. That's true. What about 2 minus 3? So if we're at x equals 2, y equals 3, we have 2 minus 3 equals -1. Wait a minute. Let's just take a second, because now I'm starting to see that, like, we're going to have infinitely many possibilities here, and I want to get a visual of what's going on. So what do I like to do? We like to, if we want to graph a line, what form do we put it in?
Standard point slope, whatever.
Slope intercept.
And y equals mx plus b.
Right, exactly. So how do I do that in this case? Well, there's a few ways. How about, I could rearrange a true equation. It should stay a true equation. Interesting. So let's bring the y over, and we have x equals y minus 1. We'll bring the 1 back over here, and we get x plus 1 equals y. So in other words, y equals mx plus b, we get y equals x plus 1. Now, let's just check for a second. We rearranged a true equation. Wait, but it's true at infinitely many points, right? Okay, well, we'll get back to that in a second. Right now, let's just get a grip on what's going on. If you gave me this equation, right, I would say, it's a line, and it looks like this. In fact, and I'm going to think about this right now as a function. I'm going to say that this thing is a relationship between inputs and outputs. When I plug in a 0 for x, I get out a 1. When I plug in a 1, and you'll notice I'm scaling this weird, but it'll be all right, trust me. Plug in a 1, I get out a 2, right? So when x is 1, you plug in a 1, 1 plus 1 is 2, so my y value has to be 2. When I plug in a 2, my y value has to be 2 plus 1 is 3. So let me get that right there. There's 3 and there's 3. We have all those points, but I know this is a line, right? Y equals mx plus b. We've been doing this for a long time now. So I can say not just those 3 points on the plane, there's actually all of them. If you were to connect every point in between, every one of those points would satisfy this equation, right? And now, just kind of as an aside, before I told you that, like, we drew a function and I said, The function isn't like the thing that we drew. The function is the relationship between the inputs and the outputs. And this line that we drew is just a map to tell me how to get from point A to point B. Well, today we're going to think about a function as something different. And it's kind of, this is one of the things, one of the big benefits about math is that, well, we could take something, an object or an idea, and look at it in two or many different angles, right? We can, on one hand, we could look at this as a relationship between inputs and outputs. And so it's a thing that maps one interval onto another interval. But on the other hand, we could say, well, this thing defines a set of points in the plane. And we want to be able to switch back and forth. Sometimes we want to look at it for 1 minute one way, and then the next minute we want to take it and look at it in a different direction. And this is one of the brain exercises that math does that will make your whole life better. Trust me, it's good exercise. So today we're going to say, well, this function or this relationship is a set of points in the plane. And we could say, and in fact, this function that I just drew right here, it is the set of points that makes that a true equation. So let's check a couple of these points. What did I say? I said, and in fact, I'm going to go ahead and do this. We'll color code this a little bit. We're going to say that f is the blue function. And yes, I drew it in black, but you can imagine these as being blue points. So this guy is f. And let's think about some of the points that satisfy f. We said when we plugged in a 0, we got out a 1. So we have the point 0, 1 is one of the solutions to that equation. The point 1, 2. So when x equals 1 and y equals 2, then we plug it into here, we can see, yeah, that gives me a true equation. Similarly, if I take the point 1, 2 and plug it into here, it gives me a true equation. I take the point 2, 3. It is on the line, right? That's how we found the point. I just had this formula. I plugged in a 2, got out a 3, so I made that point as one of them. But we can also see that that is also that pair 2, 3 satisfies this equation. Plug in a 2 minus a 3, you do get a -1. That makes it a true equation. And then there are infinitely many more of them. I don't have the time to write all of them, so I'm just going to write 3 of them. But we could see that these are the places where that original equation is true, right? Now, we've already seen that you could take a true equation, right? In order for this to be true, you have to be at one of these infinitely many different points. But then you can rearrange it and it stays a true equation. That's pretty clear, right? I mean, you believe that? Like, that's what we just did, right? Okay, that's, again, not trying to trick you. We just want to build up our belief here and say, yeah. And it's hard to think of an equation that doesn't have this property, right? You write it like this. Well, that means that there are certain points that make it true. Yeah. Okay, now subtract 1 from both sides. Is that going to change it? Well, no, it's not going to change it. It still means the exact same thing. So we could rearrange an equation. And as long as it's true at one of these points over here, then it's going to be true at the same point over there. So, okay. What about multiplying an equation by any number? Let's take this equation and multiply it by 2. Let's see what we get. I'm going to multiply this equation by 2, which of course means I'm going to multiply both sides of this equation by 2. Okay, 2x and y. Okay, so I got to distribute the 2 into here, and we get 2x minus 2y equals -2. And now, does it give me a true equation? Well, again, right, true where? We can't, let's see, like, if we plug in a 0 and a 1, okay, so if x is 0, then we get a big 0 here. Plug in a 1 for y, you get 0 minus 2 is indeed equal to negative 2. Check. What about if we plugged in a 1 and 2? Well, we'd have 2x is 1, so 2 times 1 is 2. Plug in a 2 for y, we have minus 2 times 2, and that's 2 minus 4 is negative 2. Check, still true. Do you believe that it'll work for all of the points?
Yes.
Yeah, I don't see any way that it can't. But if you didn't believe that, right, if you're like, I'm not sure, here's something we could do. We could say, well, hold up. You have this new equation. You multiplied both sides of this equation by something. Maybe it changed something. I don't know. But if you gave me that right there, I'd say, well, let's see what that thing looks like. As a matter of fact, I would put it in the form y equals mx plus b. I would say, well, let's get the 2y over to this side. And so we have 2x equals 2y minus 2. I'd say, let's take the 2 over to this side. And so we'd have 2x plus 2 equals 2y. And then I'd say, well, that's not exactly in the form y equals mx plus b. I need to get rid of that 2. And so I'd say, well, we need to divide this by 2. So if I divide that by 2, I'd have to divide all of this by 2. Lo and behold, what do we end up with? Y equals x plus 1. It's the exact same function that we have. And then I could just see it's pretty obvious that, yeah, how did we get this in the first place? Well, we plugged in x's and we got out y's. And so anyone that satisfies that is going to satisfy that as well. In other words, any point on this line, well, that's the same line. So of course it'll be true, which means of course that's going to be true right there. So it looks like we can multiply any true equation, but now we have this caveat that it can be true at infinitely many different points. And as long as we're talking about one of the points where that original equation is true, then yeah, it'll be true at that same point. Okay, so we've almost had all the same observations. And we kind of went through the thing where I contrived an example. I started off by saying, well, let's say that x equals 1 and y equals 2. And then I made up 2 equations based on that. We added them together and we got obviously a new true equation. But what happens when we have an equation that we don't know about? Like, I'm not going to contrive this example. I'm just going to make up another line. And the line that I made up was this one. Yep. Three plus y equals 3. Right away, I could see that it's a line, right? I know that it's a line. And so I'm thinking, if I put this into y equals x plus b, just like I did before, then I could get a grasp of what it looks like and what it does. So I'm going to go ahead and do that. And I'm going to say, well, the y is in the right place. The only odd man out is that 3x. So I'm going to bring him over to this side. And that's going to give me y equals minus 3x plus 3. And I'm going to go ahead and think about that as a function. I'm going to say, well, that's a function. You have a y all by itself. So that gives you a relationship between inputs and outputs. And so now I'm going to say, all right, well, let's find some inputs and outputs and see what this guy looks like. And so I'm going to start off like I did with the other one. I'm going to plug in a 0. And when I plug in a 0, for x, I get out a 3. Plug in a 1 for x, and I get minus 3 plus 3 gives me a 0. Plug in a 2, I get minus 3 times 2 is minus 6. Yeah, minus 6 plus 3 equals minus 3. Okay, so plug in a 2, get out a minus 3 right here. And then I know, right, well, this is a line. This is just a line, and it has a negative slope. It goes through here. So I'm just going to draw this guy. Okay, so that's what that guy looks like. You think about him as a function, right? Here's this function g, calling it g. And it has a different set of points for which it's true, right? Some of the ones we just said were 0, 3, 0, 3. We have the point 1, 0. We have the point 2, negative 3. And now I'm just going to kind of check my work because, I started off with something over here and then said, oh, that equation is actually like a function. So let's just check that these points do work. I plug in a 0 for x and a 3 for y. Plug in a 0 for x, we get a 0. 3 for y, we get a 3. Does that equal 3? Yes, it's a true equation. What about, let's do a little hard one, 2 and negative 3. Plug in a 2 for x, and we get 3, we get 3 times 2, plus negative 3 is the same thing as minus 3. I get 6 minus 3 is equal to 3, check, yes. And so I believe, I don't know about you, but I believe that all the points on this line, when I plug them into that equation, they turn it into a true equation. Do you believe that?
Yes.
Okay, right. We really haven't talked about anything new here, right? It's just what lines are really. And now we have like a couple ways we could think about them: a relationship between inputs and outputs, and something that gives you a true statement. And the conceptual leap now is that there are infinitely many possibilities. And so, like we said before, when we had two equations involving x, we have to be talking about the same x, right? If on one hand, x is equal to 3, and on the other hand, x is equal to 5, and then you try to put them together, you're going to get something that's false, right? We had to be talking about x being, in our case, it was 2. X had to be 2 in both equations in order to add them together to give you something that's true. So in this case, now, first off, I haven't found one place on the plane that is true in both of those equations. What we could do is, in fact, I'm going to think about this as a function. Like what I want to know, basically, so let me back up a little bit. We have infinitely many points that makes the first equation true. We have infinitely many points that make the second equation true, and I want to know, do they share a point? In other words, is there a place on the plane where both equations are simultaneously true? And it looks like there is, right? It looks like that there is some x value and some y value that's on both lines. And so what I'm saying is, and now what I'm thinking, I'm thinking about functions. And I'm just thinking, how can I find if such a place does exist? And I'm just kind of looking at the picture. I'm saying, well, if such a place does exist, then whatever it is, I'm not sure what it is. I'm trying to find this point. But it should be that if I take this x and plug it into f, it's going to give me some output value. That output value is going to be, well, this is a function, right? You plug in an x, you get out an f of x. Now, if those two places touch, right? That is, if this is true both times, then when I plug in that same value of x, whatever it happens to be, then when I plug that into G, I should get the exact same output.
Mhm.
All that means. That's what that means. So in other words, I'm asking myself, is there an X value so that when I plug it into G, it gives me an output? We could call it Y. Special value of Y, not any old Y, there's a special Y. And we want to know if I take that same X, the red X, and plug it into F, will it give me that same output value? And now thinking about this in terms of functions, we can say, well, now symbolically, what you're asking, Justin, is you're saying, is the output of G the same as the output of F? Right? We want to know, is there such a place? Is there an X so that the outputs are equal? In other words, is there a place where G of X equals F of X? If so, when I do this, I should be able to find that value. Why? Well, let's think symbolically here. G of X represents the output, the Y value, right? And that's what we're saying. There's an output value here. How did we get it? Well, remember, when we plug stuff in, we just plugged it into here, right? So symbolically, we're saying G of X here is minus 3x plus 3. That needs to equal the same output as X, right? So we're saying the height of this with the same input X needs to give me the same output Y. Well, that output has to equal that output. So we're just saying that right there. Now we have one equation involving one variable, and well, we could solve for that variable. I'm going to take 3x and add it to both sides. That kills that, and I get 3 equals 3 and 1 make 4 x's plus 1. Subtract the 1 from both sides, and I get 2 equals 4x. Divide both sides by 4. And we get that x is equal to 2/4, or how about x equals 1/2? Okay, so what we just found is that when I plug in x equals 1/2, and this is kind of nice because if my pictures, the functions that I graphed, if this is all consistent and works, then it had better be a number somewhere between 0 and 1. And it sure looks like it is. It looks like if we let x equal 1/2, then the output of G should be the same thing as the output of F. Let's see if that's true. I'm gonna erase this work right here. Are we good to go?
Yes. Wait, hold on. One minute.
Go for it.
Okay.
Actually, give me just a second. Okay. So let's check that we do get the same output from each of these functions. And then we could find what the output is, and then we could find the point. The idea is there should be a point which makes both of these equations simultaneously true. And we're going to end up checking that. We need to find what the output point is, right? We need to find the Y value. So we have X as a possible input value. Let's see if it works. And we want to see, does G of that X equal to F of that X? And so let's do G first, since it's on the left. When I take X and plug it in, G of 1/2 is equal to -3 times 1/2 plus 3. -3 times 1/2 is -3 halves. 3 is the same thing as 6/2. Want that common denominator there, so I just rewrote 3 as 6/2. Now I have 6 halves minus 3 halves. 6 apples minus 3 apples is 3 apples.
And so we have positive 3 halves. Okay. That's our possible y. That's our possible output. Now it has to be that f equals the same thing. Now, if you're clever, you could say, well, Justin, we already did that. That's how we obtained the original, that's how we obtained 1/2 equals x. Well, let's just check. I want to make sure, okay? So I'm going to say f of 1/2. I want to make sure we get the same exact output. Okay, so I'm going to say f of 1/2 says we take 1/2 plus 1. Well, that's the same thing as 1/2 plus 2 halves. 1/2 plus 2 halves is a total of 3 halves. And so, yes, that must be my corresponding y value. The y must be 3 halves. In other words, the red y, that special y that we were looking for, should be 3/2. That should be the point. In fact, I'm going to go ahead and make him red right here. That should be, and we can say this a few different ways. That should be the point on the plane where the two graphs or the two functions intersect. And it should be the point that makes each of these equations simultaneously true. Because there's one thing we didn't say, and I want to do this real quick. Can I go ahead and get rid of the work here?
Yeah.
Now that we have that x equals 1/2 and y equals 3 halves. Okay. Oh man. Equals y equals 3 halves. Okay, now, because just to be sure here, let's take one of these points, like this one, 0, 1, that we know works for the first function. If I take the point 0, 1 and plug it into the first function, I get 0 minus 1 equals -1, and that works. But that point does not work for the second one, because when I try to plug it in here, I get 3 times 0 plus 1 is 0 plus 1. That is not equal to 3. If I take one of these points, one of the green points, right? One of the points that's a solution to the second equation, and I plug him in. Let's take the point 1, 0. That'll be nice. Plug in a 1 in for x and a 0 in for y. I get 3 plus 0 is equal to 3. Yes, second equation is true. If I try that same point at the first one, I get 1 minus 0 equals -1. 1 does not equal -1. So it's not, the two equations are not simultaneously true at these points. We're hoping that they will be simultaneously true at 1/2, 3 halves. Let's check. I mean, we already know it is. I just really want to beat this dead horse because I want us to believe what we're about to do. Okay, so let's just check that what I have just done gives me a point that solves both those equations, or rather a point that makes both of those equations true at the same time, at the same point. So I'm going to take the point x equals 1/2, y equals 3 halves, and plug it into each of these equations. In the first case, I get 1/2 minus 3 halves. That's 1 of something minus 3 of something should be -2 of something. So -2 halves, which does indeed equal -1. So the first one checks. Plug it into the second equation, we get 3 times 1/2 plus 3 halves. 3 times 1/2 is 3 halves, plus 3 halves is 6 halves. 3 plus 3 is 6, yeah, 6 halves. 6 halves, that's 6 divided by 2 equals 3. Oh, lo and behold, we found the point on the plane that makes both equations simultaneously true. Now, it sounds like, okay, all right, I think I have an idea of what we're going to be doing now. No, you don't, because because unfortunately, like,
If the only thing we ever cared about were systems of two equations with two unknown variables, if that were all we ever cared about, I would say do this every time. Every single time, just get y by itself, set the two output values equal to each other, find your original input value, take that value and plug it in to find your output value, and it will work every time. And that's true, it will, when you're working with two equations and two unknowns. When you have three equations and three unknowns, it gets ugly, really ugly to try to do this. Because now you're not just working with two equations and you just set those two equal to each other. Now you have three equations. And so there's a bunch of different possibilities of setting them equal to each other. Guess what happens when you have four equations and four unknowns? What about five equations and five unknowns? How about 100 equations and 100 unknowns? So this method, while it's beautiful with two variables, it works every single time with two variables, it will not help us establish a method for doing systems of equations involving more than two variables. So that's not what we want. What we want is a method that's going to work no matter what. And in order to do that, we're going to use these observations. Now, what I want to do real quick. So, okay, we found the point where it's simultaneously true. Now, what I want to do is verify something real quick. So what I said here, I'm going to go ahead and erase the work we did to verify that the point 1/2, 3/2 is a solution, or rather is the point where both of these things are simultaneously true. And what I want to do is just kind of test our other observations here. We've seen that we can rearrange an equation and it stays true at the same points. We can multiply these equations by any number and it stays true at the same points. We get a new equation when we do that, right? This equation is not the same thing as that equation, but it's still true at the same points. We multiply an equation by some number. It's not exactly the same equation, but it's true at exactly the same points. Now we add two true equations. Remember the very first thing we did? I contrived an example where I said x equals 1, y equals 2. And as long as that was simultaneously true, then we added it together, got a new equation, and it was true at that same point. That's what's going to be true here. We're going to, if we were to add these things together, well, first, let's just, I kind of want to, again, beat a dead horse and say, if I multiplied this first one by 2, okay, so I'm going to take the first equation, x minus y equals -1, and I'm going to multiply the entire equation by 2, which means multiply both sides. 2x minus 2y equals -2, and we know that that's the exact same line as f of x here. Let's just take that and add it to my second equation and see what happens. We get 3x plus y equals 3. Now let's just add them together. 2x plus 3x, we have 2 apples and 3 apples make 5 apples. We have -2y plus y gives me -1y. -2 plus 3 is a +1. I'm looking at that and, oh boy, that's a new equation. It's not either of these equations. Well, wait a second. I want to wrap my head around this thing. In fact, I'm going to put it into the form y equals mx plus b. I'm going to do that by taking the y over to this side, giving me a 5x equals y plus 1. And then I'm going to subtract 1 from both sides to give me y equals 5x minus 1. Now I'm going to graph this guy and say, okay, when I plug in a 0, I get out a -1. It should be around here, -1. When I plug in a 1, I get a
1 times 5 is 5 minus 1 is positive 4. So when I plug in a 1, I get out a 4. And I could keep going, but now I can see that this gives me a line. And I wonder, I wonder if this line is going to go through that same point that I cared about. And I'm just going to kind of think back to the very first thing we did when I contrived an example and added two things. We knew that the two equations were true at the point 1, 2. When we added them together, we got something that was true at the point where they were simultaneously true. I'm willing to bet that this new thing that we got, this new equation, is true at the point where they're both simultaneously true. And this really comes from this observation earlier. It's like, well, yeah, if they're both true at the same time, you add them together, the new thing you get should be true at that time or at that place. Because once you plug that number in, you have something like 2 equals 2 and 3 equals 3, and you add it together, you should get 5 equals 5. Right? So let's just check it. Let's check and make sure that when I plug in our special point into this new equation, that we do get something that's true. So when x equals 1/2, I get this. And when y equals 3/2, I get this. So you see what I'm doing, right? I'm starting with the original equation that we got, right? When we just added those two equations together. And now I'm checking to see, is it true at that point? And so I plug that point in and I get 5/2 minus 3/2. 5 minus 3 is 2, so that gives me 2/2. 2/2 is equal to 1. And so yeah, that is equal to 1. Verifying in a different way. I'm going to take my line, my function, plug in 1/2 and make sure I get out 3/2. So I'll do that right here. I'm going to say we know that y equals 5x minus 1. When x is equal to 1/2, I get 5 times 1/2 minus 1. So I get 5/2 minus 1, the same as 2/2. 5 minus 2 is 3, so we have 3/2. So we find that yes, when x equals 1/2, y equals 3/2. So this line that I drew, this new line that I obtained by adding the two equations together, is true where both of those equations are true. Do you believe that?
Yes.
Okay, like we used specific examples here, but do you believe that that's going to be the case whether I did it with any example that I do?
Probably.
Probably. Okay, that's an honest answer. I love it. And we could prove that it is the case, right? It's not hard, it's just a bit abstract. And when you see it, you're like, I don't know, I guess you proved it. That seemed a bit too simple. And it's true that, yeah, if you do that, yes, this line is true, just like the other ones, at infinitely many points. And so we have infinitely many points here, but there happens to be a point where both of our original equations are true. So when you add them together, you get another line that's true at infinitely many points. Most of them are different, but the one that we care about is still true.
Mm-hmm.
Almost done. We're not even close to a method yet. Well, we're kind of close. We're kind of close to the method, but we need this one last observation. Like I went and took the first equation and multiplied it by 2 before I added it to the second equation. Let's add the equations together and see what we get. So I'm going to erase this stuff. Let's just add these guys together. See what happens. Okay, I'm going to take the first equation plus the second equation. 3x's plus 1x gives me 4x's. My y's cancel out. That's convenient. That's really convenient. That negative y plus y gives me a total of 0 y. positive 3 minus 1 gives me a positive 2. And I'm left with 4x equals 2. I'm left with an equation that is true exactly where both of the equations are true. What do you know? I just happen to add it together in a smart way. The first way didn't help me, and I got something that was like junk. I had to like go and graph it and stuff like that. It happened to be true, but I didn't really help my case anymore. I'm still kind of I'm still, I could throw away one of these equations, I guess, but now we're still trying to find the intersection of two lines. But when I add these together smartly, when I'm clever about it, I could say, hey, you know what? If I just add these two together, that variable is going to disappear. And I'll be left with the equation of a line in one variable. And so in other words, I will have found that special point right there where both of those original equations were true. I could use this principle again and say, well, I can multiply an equation by any number. I can add them together, and the point that we care about, the point that's simultaneously true for both of them, whatever I get out, this new equation will be true at that point. So if I want to find that point, well, let's do this. It's like, I noticed that when I had a negative y, a plus y, they canceled out and gave me just one of the variables I'm looking for. So I'm thinking, if I could get these two to cancel out, right? And I don't want to think too hard about this. It's just, I noticed that's a positive one, that's a negative one. If I want these to cancel out, that's a positive 3. What do I need right here? How do I get rid of a positive 3? What do I add to positive 3 to kill my positive 3?
Negative 3?
Negative 3. So it's like, if there were a negative 3 in front of that x, I'd be good to go. How do I get a negative 3 in front of the x? Well, I could multiply an equation by any number. So how about I multiply that top equation by negative 3? Let's see what happens. I have x minus y equals negative 1. I'm going to take that and multiply it by negative 3. Do that to both sides. And I get my new equation, which is minus 3x plus 3y equals positive 3. Now, we already know that that first one gave me that. Okay, now I'm going to take that first equation and add it to my second equation, kind of using the same trick. It's like, well, I noticed that when I had opposite numbers in front of these guys, they canceled out and it did me some good. So maybe I could do the same thing here. And so let's do that. We're going to add these together. The positive 3x and the negative 3x cancel. That's by design. That's what we wanted, right? When we're trying to make one of these variables drop out. It does, and now I get 3y plus y is 4y. 3 plus 3 is 6. How about I divide both sides by 4? And I get y equals 6/4, but 6 is 2 times 3. 4 is 2 times 2. So I could reduce this guy by clearing those 2's, and I get y is equal to 3/2. Lo and behold, what did I do? I multiplied an equation by any number, and it gave me another equation that was still true at that point, right? This new equation is exactly the same thing as that original, that original equation. So it's still true at that point. Added them together, and it gave me a new equation that's still true. It's a new line. It just happens to be a flat line that is true at the point we cared about. We did the same thing in order to get x. And so this suggests a method. Now, like I said, at first, it's kind of like, it's like, seems a little weird, right? Like, in a sense,
well, I'm not sure if it seems this way now, but when we start doing examples, it'll seem like you're doing more work using this method. But the beautiful thing is doing this kind of thing, this is eliminating variables, and this is really all you have to do with 2 equations and 2 unknowns. It gets a little bit more difficult with 3 equations and 3 unknowns, but it's going to give us a method that's going to work for any system of equations with any number of variables and equations. And we're not there yet, but now we've built up the idea, right? Which is like, well, we could rearrange any equation. Yeah, we're not really going to use that. It's more that we can multiply any equation by any number. We could add 2 equations, and the thing that we get is still true at the place where all of the equations are true, which is ultimately what we're trying to find. So, do you believe this?
Yes.
Right. Okay. That's all I wanted to do today, because I could have just gone right into the method, right? And like, I've learned this stuff before. Like, I know and that's what they do usually. They just go right into, this is how you solve it. You just do this and add these together, and now your thing pops out. It's like, why? I don't see why that works. It doesn't make sense to me that I could just add 2 equations together, and if 2 of the variables happen to cancel, now I have my answer. Well, it's because of this principle, right? That everything we've just been talking about. That's why it's true. Now we have a foundation for why this stuff works. Now we just need to hammer out the ins and outs of it. And we're going to, and like I said, we're going to end up with an algorithm, and it's mostly mindless. It's you pretty much, once you believe that this is true, you don't need to use your brain except for like adding, subtracting, and multiplying. It's really all you're doing after that point.